Hi, so today's task is find mode in a binary search tree. Let me quickly read the problem statement. So the easiest one um, is to walk through the BS binary search tree and save the elements into the frequencies of the elements into the array, frequency array, and store the maximum frequency also, like index. And whenever like a new, what if there are a couple of the most frequent occurred element like duplicates, like 3 occurred like 5 times and 5 occurred also 5 times? Um, okay, let's do that. I assume in this case I should return any. Oh, return them in any order if there are more than one mode. Okay. Okay, so I probably don't need to do that maximum frequency saving. So the first idea I have is to walk through the binary search tree and save the frequencies there, and then walk through the frequency array and check what the most frequent values, and then save it into the output. Say private DFS, and then 3 node, and then I'll do what I'll do, and I'll have, let's say, okay, integer frequencies. If not equals null, I'm just gonna return. If else, I need the frequency node.val plus plus, and then DFS node left, then DFS node right, and then I'll do the following. I'll create here array int frequency array integer, so max 10 to the power of 5, 2 by 10, uh, so let's say 4, let's say not val plus uh, In the range, number of nodes in the tree in the range 10 to the power 4. 1. Okay, and here we get 10. Okay, and I do DFS root, and then for int I equals int max fk equals 0, while for int I equals 0, I less than fk length I plus plus max fk equals max. Mm, I can do the counter actually here also. If fk e equal max fk, then counter plus plus, else if fk e greater than max fk, then counter equals 1, and then max fk equals fqy. And then int output equals new int counter for int I equals 0, I less than fk length I plus plus, if fqi equals max fq, I'm gonna add output and um, then return output. And also I need to subtract, when I gonna add to the output, I need to subtract 10,000 because I was adding 10,000 here. Oh no, I need basically from I need subtract I. Mm, Hmm. Okay, so let me check what's the minute of this. So it's 11th minute. So what I can do right now is to try to beat this problem in terms of like the time complexity and the space complexity. The time complexity seems like here I'm doing extra operations for the figuring out what the max frequency. Usually I can do that with something like this int max fq, and then I can have int max fq equals 0, and then I can go path max fq, and then here also max fq. um, and here also max fq. So for the max fq, I can actually undo that. So also I'll say it's meta. The meta first one gonna be max fq, and second one gonna be counter meta. Here meta meta. Let's say if new frequency new frequency greater than meta, then max frequency, then meta meta 0 equals this frequency, then meta 1 equals 1. Else if they're equal, I'm just gonna save meta 1 plus plus. So I'll pass meta there. And now we don't need this. you can use this out of meta. Yeah, a little bit better, but still kind of not that good. So the idea behind like constant space, if you don't account for the if you don't account for the whatever they say um, stack space, so the constant space. So here I'm using this frequency array. That's how the size of the uh, tree, and it saves for the every node. It saves the frequency, so it's like space of n currently. Plus I go through the binary first through the BFS, not BFS, binary search tree, uh, BST through BST, and that like if it's valid binary search tree and if it's balanced, so the stack space will be log n space complexity plus we have frequency n. But in case the binary search tree is not balanced, it means that Alden might be also off and in case it's weighing binary search tree. Uh, so the general idea for the most frequent the element that frequencies that has the most frequent um, the elements that occur most frequently um, so let's say we have 1 2 2 here like this, like 1 then 2 and then I wonder why they do that. Okay. Um, so let's say we have binary search tree here. Um, so we have 1, then we have 2, and then we have like 2 here. So the idea I have right now is to return the most frequent element back and its frequency. So we go like through 1, we go through the 2, and if we reached I reached the leaf node 2. So I do the following. So the idea is that the modes, like similar elements, like the same elements, they're gonna be on the same kind of weighing. Yeah. Um, so in case we have Um, it might be not true actually. They can be like in both veins, yeah. If you have like we need to somehow balance like this long binary search tree. If you balance it like this, that's a good question actually. How the binary search tree is balanced for the duplicates. Let's search it. Okay, we store just the frequency. Okay, I got it. For the balanced binary search tree, we just store the frequency. Let's ask again, double check. Mhm. Just save the counts. Yeah, that makes sense. So, but we don't have balanced binary search tree here. We just have BST that can be like Wayne, like here. So, my my current solution that I have in mind, it 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 based on the fact that the same elements gonna be on the same vein, and I can just percolate it up to the top with the value for the uh, val for the value and the val FQ. This like tuple I can percolate it to the top, and whenever I have the situation of uh, like let's say we have this binary search tree one, here we have let's say 0 -5, and here I have like let's say I have can it be like this? I wonder. So in this case I need to go -5 gonna be 1 minus 1 gonna be 1 frequency, and then at 0 I need to decide which one I will take among two, or should I take itself, or should I take actually 0 also. So in this case I assume I should do this, take all of them, 0 1 and then 1 1, and then here at 1 I can find the 1 here, and I can increment it by 2, and I can take it out as a maximum, something like that. Yeah, the only question is, can I really have this? Is it a valid binary search tree? like this one that can have like duplicates. Is it a valid binary search tree? Where valid. So let me read the problem statement here. It is not contain only nodes with the keys less than or equal to the node's key. The rest of trees is greater or equal than or equal to the node's key. Okay, so like left and right is greater or equal or less than equal. So based on this definition, this is, I guess, valid binary search tree, and we need to maintain this frequency array. Yeah, something like this. Let's say we have can basically optimize it for the so it's gonna return hash map with the frequencies integer, and then DFS node. So I will do the following. So I need to DFS right, DFS left, and then um, and do save the hash map of the frequencies. Right, left hash map, left map, let's say, and then do the same right map. And then I need to merge it and save only the one that's that most frequent, including the current value for the node, or the couple that are most frequent. It's kind of difficult right now to do this. Let me think about, maybe I can simplify it a little bit. So because this is, we allow duplicates that will accumulate this frequency array. how we can get rid of this situation, because I wanna like reduce this frequency array as much as possible as I go up. Can it be a situation like this? No. Okay, let me try this one. Hash map, and then let's say we have for int key int left map key. Okay, let's have this result hash map. Integer merged equals new hash map, and then merged get or default for the node, let's say merged put node val, then 1, and then for integer key in the left map key set, I wanna do merged get or default key 1 0, then plus 1, not plus 1, plus left map get key. Merged put key. For the key, I wanna put this incremental value, and I wanna do the same for the rate. Let's say lmap, lmap, and then lmap here, lmap here, rmap. And then I wanna go through the merged, and then I'll say max frequency equals 0, max fq equals, let's say 1, max fq equals merged get key. And do the same here. And then I wanna hash map integer output equals new hash map. And then I wanna go through the for integer key in the merged key set. I wanna check if the merged get key equals max of q, and if so, I wanna add that to the output. Just like that, and then return output. And then in this function dfs, I can get the hash map and then int output equals output, I'll say hash map key set that size, and then for int I equals 0, for the integer key, the hash map key set. I wanna save that to the output ptr ++ equals key, and then return output. So the sketch for the solution, I try to save the frequencies of the left and the right subtrees, and then add the current node, contribute that current node to the merged frequencies. I merge them and I get the maximum frequency element out to the top. And then I do that on every level, and then I'm gonna have a hash map of the modes, and I need just save it to the output. Mm. Not working right now. wonder why. So let me draw this example. So we have the new, so I have 6, then I have 2, 8, then 0, then 4, then 7, then 9, here's no, here's no, here's okay, 6, 2, 8, 0, 4, 7, 9, then okay, null here, null, and here 2, and here we have 6. So in this case, I should percolate. Okay, I get rid of the 6 on this level, and like right here. So I have 2 frequency 2, and I have 6 frequency 1, and that's why I remove it from the merge. Um, and then when I come here, I need to to have it still there 6, so that 6 frequency becomes like 2, and we'll have the output 2 and 6. Instead of this, I just remove 6 on this level, and that means that I cannot percolate it to the top, and my return is like just 2, and it's incorrect one. So how I can efficiently like reduce the number of uh, the elements I percolate to the top. I tried this approach, but it didn't work. So if I go to the left subtree, the range gonna be 6 and then something. And then if I go to the right subtree, the range gonna be 6 and then from 6 inclusive to something. Then if I'm gonna go to the 8s, if I go to the 8s here, so the gonna range gonna be 6 to 8, and here if I go to the range here, the range gonna be 8 something, and then here I'm gonna have 0 something, and here I'm gonna have no, if I'm gonna go here, it's gonna be 2 or something or less, and here I'm gonna be greater than 2, less than 6. And here, if I go here, it's gonna be 2, 4, from 2 to 4 inclusive. Here gonna be from 4 to 6 inclusive. Yeah, my assumption was that the modes in a binary search tree gonna uh, stay on the vein and they're gonna be like follow the vein, but it seems like currently there is a gap, at least here between this 6 element and this 6 element and this 6 element. There is basically a gap. Um, there are a different element in between. So like if I connect it through the vein, it's gonna be 6 to 4, 6, and I assumed it's gonna be just also all 6 through there from root to leaf. That was wrong assumption. I can still solve it with constant memory. It seems there is a Morris traversal algorithm that, huh, that's interesting. Okay, I I don't know. I didn't know that. I've heard about this algorithm, but yep. Okay, I probably need to wrap up. This is pass, but because I didn't know Morris traversal, I feel I have mixed feelings. Yeah, definitely nice to read this one. Will I'll read it on my offline. Okay, that's gonna be wrap up. I'm gonna wrap up and generally pass because I managed to solve it within like first couple, like maybe 10 to 15 minutes. But I didn't know how to traverse it with a constant space, not counting the stack. So yeah, that's it.